Next we've got Florian. He's going to talk to us about this. Over to you, Florian.
Thank you. Hey everybody. Today, or for this brief 20-minute slot, I'm going to talk a little bit about Ceph, which is a distributed storage stack, and its integration with OpenStack. It is not the only Ceph talk that we have all week. We already had the Grand Distributed Storage debate in the Cloud Distributed Storage and HA MiniConf yesterday, where we had Ceph and GlusterFS kind of go head-to-head. Sejawal, the original author of Ceph, is doing a Ceph talk in the main track of the conference, I believe, on Wednesday. And there is also a Ceph tutorial, full Ceph tutorial, that yours truly and Tim Sarong are going to be doing on Friday afternoon. So if you want to learn more about this, then by all means, please come to our tutorial on Friday. So what is Ceph? Ceph is actually not one thing, but is 4 different things. And out of these 4, I'm going to highlight 3 here, because only 3 of them are actually relevant to OpenStack, or as general purpose storage for OpenStack. Ceph is fundamentally, at its core, a native object storage solution. Not unlike Swift in that architecture. It implements the idea of object storage very, very differently than Swift does, but it still operates on similar principles, such as at the level where we're talking about distributing and replicating and balancing data. We don't really need to worry about things like are common to POSIX, such as a hierarchy of directories and nested directories and files in them, or permissions of any very intricate nature, or a lot of, we don't need to pay a lot of attention to ownership. All of these things can be very simple, and the operations that we apply to our data can also be very, very simple. It's essentially boiling down to get, put, delete, that's it. And what Ceph does is it implements such an object store natively. The universal unit of data storage is not a file, is not a block, it's an object. And those objects are automatically being distributed across the cluster, and the cluster can scale to hundreds of nodes and petabytes and exabytes of data if we want to. And they are also replicated in, they are stored redundantly in a very highly configurable fashion. And then everything else that we're talking about in Ceph are essentially this. We can use the object store directly. There are a bunch of library bindings for them. We can talk to the object store directly in C, C++, Python, whatnot. But most of the time, we're going to be using, and OpenStack uses, one of the more high-level API layers that we can use to interact with the Ceph stack. One such thing is we have a block storage client layer on top of Ceph. What we can do with something called RBD, RADOS block device, is we can expose block device semantics to a client either in the kernel or in the virtualization layer, where we're presenting to that layer just a block device, and then that client layer driver translates all of the I/O to that block device to I/O on RADOS objects. And then it inherits all the capability from the underlying object store about distribution, replication, redundancy, etc., etc. Those block devices can actually be pretty smart. They're thin provision in Ceph. They support very cheap and inexpensive snapshots. We can clone them. They support extensive caching, etc., etc. But it's just a client layer on top of the native object store. Another thing that we can do with Ceph is, and here's where it gets very, very close to Swift, we can use Ceph for RESTful object storage. So there is a facility called RADOS Gateway, which allows us to interact with objects in the store directly using RESTful APIs, using HTTP, HTTPS, and JSON, where we can use S3 and Swift client APIs, actually, and client tools to interact with this object store, and we can do that in a very scalable manner.
Layer called?
That layer? The question was, what's this layer called? The layer is called RADOS Gateway. in Ceph. And then finally, we have the thing that most people automatically sort of associate with Ceph and what Ceph originally comes out of. It was originally built as a distributed file system. And that file system, too, is just a client layer on top of the object store. And this is what does all of the interesting stuff that is relevant for POSIX, such as directories, and ownership and permission bits and all sorts of things. And again, the file system here does not have to worry about the balancing, etc., because all of that happens at the object store level. So let's get into that in a little more detail, and not as much detail as we're going to go to in the tutorial on Friday, and not as much detail as Sage is going into in his talk, but still, just a few little pieces, and I'm going to start with the native object storage bit. So Ceph is based on a distributed, redundant, and autonomic, meaning self-organizing, object store named RADOS. And RADOS stands for Reliable Autonomic Distributed Object Store. Now, what's interesting about RADOS is it is a completely flat namespace. So like I said, there is no such thing as a directory hierarchy or any of that nature. Every object in Ceph has a name. It has a payload or content, and it has an essentially arbitrary number of key value pairs, attributes, that we can tack onto the object. And objects can be of almost arbitrary size. I say almost because if we go beyond a certain threshold, then we will just stripe across multiple objects. These objects are assigned logically to what we call placement groups. And every placement group has a list of, depending on whether we use the outdated documentation where it sometimes says object storage devices, or we use the new documentation, object storage daemons, it all basically reduces down to OSDs. And on these OSDs, the contents are stored, the contents of all the objects in this placement group are stored in a redundant fashion. And why is it an ordered list? Because it uses essentially a primary copy means of writes. So a client knows, okay, what is the first entry in the OSD list? That's the one I'm writing to, and that OSD is then responsible for replicating off to the various replicas. And how many replicas we have is completely configurable in a very, very flexible manner. The interesting thing is that the entire object placement is completely algorithmic. So there is no central lookup instance, like, for example, a metadata server in Lustre would be. There is also not a distributed hash table as we have, for example, in GlusterFS. It uses an algorithm called CRUSH, Controlled Replication Under Scalable Hashing, and we can use this algorithm to define in a very, very flexible manner our replication and balancing topology in the cluster. By default, and the interesting thing is that pretty much everything in the center of this algorithm, that includes the OSDs, the storage portion of the cluster itself, and also clients, and the only thing that we then need to feed the system are the parameters to this algorithm. And those parameters are expressed in something that we call the crush map. So that's basically the rule set that we define how data is placed and where data is retrieved. So by default, Ceph uses a simple crush map that just makes sure that when we distribute data, no two copies of the same piece of data are stored on the same host. But we can extend that and can say, well, we actually want to spread our cluster of perhaps several hundred nodes and several exabytes over 3 physical locations. And we want to make sure that we have one copy of each little blob that we put in there in each data center, so that at any time we can literally have an A380 crash into any one of these data centers and take it out completely, and we're losing a single bit of our data. How this is done and how this actually works internally is something that I regularly completely geek out about. Very unfortunately, I don't have time to cover that in detail in this talk, but if you want to geek out with me, then please by all means come to Tim's and my tutorial on Friday, where we're going to go into it in a little more detail, and you also get to play with it live on Ceph boxes that you run. But this is really, really, really cool stuff. And there's a lot of intelligence that is actually built into the Ceph storage architecture itself, such that it essentially operates under the assumption that at a certain scale, something always fails. And that's okay. The system can recover from this very, very comfortably and very, very nicely, which is really, really cool. Ceph is obviously built for big data, or more precisely, really for gigantic data. It works just as well for not quite as gigantic data. So if you're building a cluster of maybe a few hundred gigabytes, or maybe a few terabytes, or tens of terabytes, it works just as nicely, and that's really cool. We have lots and lots of client APIs that we can use to interact with the Ceph object store. We have a C library called librados. There is a C++ version of the same called librados pp. We have Python bindings. We have scripting language bindings and whatnot. We have command line tools that we can use to interact with the object store directly, etc., etc. So if you have a need for an application, or rather a piece of storage that you can use, plug into an application that will basically take care of all of this distributed storage for you, then you can just use that. But if you're not a developer and you're just looking for a predefined use of the Ceph object store, there's plenty of these. And those rather high-level client APIs are what is typically used in OpenStack when we integrate it with Ceph. And the integration between these Ceph parts, API parts, and OpenStack is an ongoing one. The folks at Inktank, that is the company that pays most of the developers that work on Ceph, not all of them, but most of them, are very well involved in the OpenStack community process, and there is an ongoing integration work into several bits and pieces of OpenStack. And I'm going to run through this in a second. The first thing that I want to cover, because arguably it is the one where most people that are using Ceph and OpenStack see their need for integration, is block storage. So in Ceph, we have this thing called a Rados block device, and those are thin-provisioned block devices that stripe data that is written to them across multiple Ceph objects, multiple Rados objects. So when we write data into this thing, we can work with it as if it were any old block device. But what happens under the covers is that the I/O to these blocks that we're working with gets translated into creation or modification, etc., of Ceph objects. And then we can do cool things with that. So means that when we create a new block device of, say, I don't know, 10 gig, for the sake of argument, then the amount of data that is being allocated at that time is exactly one Rados object, which is an object that essentially holds a little bit of metadata about the RBD. And then as we write into it, only as we write into it do we actually see Rados objects getting allocated and written. So thin provisioning. The next thing is snapshots. Because all of these objects are essentially thin provisioned, because we don't need to think of an RBD as this one contiguous chunk in the object store, from that it follows logically that we can also very, very cheaply and easily do redirect on write snapshots. These snapshots are read-only, but we can do something called cloning. And cloning means that we're essentially taking a snapshot, defining it as a master copy for other RBD images, and those RBD images are then writable. Does that ring a bell for anyone who's familiar with Glance? Kinda, sorta? Huh? Which makes that an excellent fit for things like template-based virtual machines, which is what we use in OpenStack all the time, right? We want to be able to take a running virtual machine, take a snapshot of it, toss that snapshot into Glance, use that as a reference image, and the next time we say Nova boot, la 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 la, boot off of that, or create a new clone off of that image, and off we go. So that is something that lends itself very, very naturally to integration with RBD. RBD actually comes in two flavors, depending on which OpenStack compute hypervisor you're using. You're probably going to use either the one or the other. The one that was there first was a kernel-level block device. So this is something you initiate a process called mapping. And as soon as you map an RBD image, it simply becomes a block device, a virtual block device in your Linux box. It pops up under dev RBD, and then you can use it in any way, shape, or form that you could use any regular block device. You can make a file system on it, you can write directly to it, whatever you like. That went upstream in 2.6.37. However, that is not what you typically use in OpenStack, for the simple fact that most people will be running OpenStack using libvirt and QEMU KVM as their hypervisor. If you're not, if you're using Zen, for example, that would be your preferred choice. If you are actually running on QEMU or KVM, there is something else, and that is the QEMU RBD storage driver. It is part of upstream QEMU and hence KVM. It is fully supported in libvirt as well. It is itself based on one of the client APIs that I previously mentioned, librados, simply because QEMU is written in C, and that's the natural fit. And what that does is it allows you to essentially run or provide an RBD storage image directly to QEMU using the RBD storage driver. You're most probably familiar with two storage drivers for QEMU. One is file, which you use just a file-based image, and one is the physical one, PHY, which means you're actually using a block device. But that storage driver architecture in QEMU is actually pluggable, and this is one of the plugins that are supported. So you can run QEMU KVM directly off of an RBD image, and that is also supported in conjunction with both libvirt and with Nova, as we're going to see in a second. But for right now, Glance, this is fully integrated with RBD. It's really, really simple, if you have a running Ceph cluster, to switch your Glance to use that Ceph object store for RBD image storage. Essentially, what you define is, okay, what's the CephX user, which is essentially a shared secret to connect to the Ceph cluster. We define what is the Ceph pool where we're storing the images. Boom, off we go. And then it works roughly like this. When you're interacting with Glance API directly, such as if you're creating a new image, or you are downloading an image from somewhere on the web and you want to toss that into Glance, you just use the regular Glance image create whatever command, or you do the same thing from the Horizon dashboard. And what it will do is it will just completely transparently create an RBD image for you, pump the data in there that you want to have in there, and then that is an image that gets a UUID that shows up in Glance image list, and you can use that like any Glance image that you would otherwise perhaps store in a directory, which is the default implementation, or would store it in Swift. And then when Nova boots, it will actually take it also essentially talks to Glance, getting the image that it wants. And this is actually smart enough in latest versions of both Ceph and Nova Compute that if you are, do I have a slide for that? No, I don't. That you can actually do a direct boot from volume from that copy, which is really, really cool. It is also integrated, RBD is also integrated with Cinder. Cinder is the block storage layer that we have in OpenStack, or the block storage subproject that we have in OpenStack. And that used to be called Nova Volume. It's an independent project as of Folsom. And that is also fully integrated with RBD. And there we also have the integration with Nova for boot from volume, which is cool. And this is what makes this combination particularly appealing to those who are looking for OpenStack essentially to run a private cloud, which means they are running they're looking for or implementing a modern way of running a data center. Is essentially what it is. We don't want to deal with iron and wires anymore. We want to have fairly standardized installations everywhere, and then we want to keep going, deploying workloads. So here's how that works. When we need to talk to Cinder API directly, then the integration with RBD goes through Cinder API, such as I'm creating a new volume and whatnot. And if we have Nova actually talk to these, then it doesn't need to go through Cinder API. It just goes through Cinder API to figure out, okay, what do I need to connect to? And then it is actually Nova itself that and then uses these RBD images. RESTful object storage, that is something that we, of course, have in OpenStack already. But what we can do with Ceph is we can use Ceph as a drop-in replacement for Swift as well. Here's how this works. There is a RESTful HTTP or HTTPS access gateway into the object store. It's called Rados Gateway. It is a FastCGI application. It's built on the librados PP C++ API, and it generally runs essentially with any web server that supports the FastCGI interface. The canonical way of doing it is with Apache and Mott FastCGI. Theoretically, you can do it with anything that supports FastCGI. Theoretically, that would include IIS. No, I would not necessarily recommend that. The cool thing about Rados Gateway is it did not really invent its own wheel in the sense that, how about we write our own RESTful API? No, it went and implemented existing RESTful object storage APIs. How about that? It supports both Amazon S3 and OpenStack Swift. And it does so in a fashion that I can actually take an Amazon S3 client, create a bucket, put an object in there, and then take a Swift client, address that bucket as a container, and retrieve the object from it using appropriately matching user credentials, which is cool. Just like the Swift proxy server, Rados Gateway supports native load balancing and scale out in the sense that it actually doesn't store anything locally. All the Rados Gateway relevant data is in the Ceph object store itself. So that means we can have as many of them as we want, and we can load balance them with round-robin DNS or with an IP load balancer or whatever we want, which again is kind of neat. By the way, the same thing is obviously true for Swift proxy. So there's no, it's no better than Swift proxy here. It's just feature parity. There we go. And something that's relatively new is it actually does support keystone authentication. So just like Swift, which originally had its own authentication API and then grew keystone support, the same thing was true for Rados Gateway, except that it trailed Swift by several months. But we have that now, so we don't need to use separate authentication when we're talking to Rados Gateway, but instead we can just use our keystone credentials and go with that. So that's how that looks. We have an HTTP client, any HTTP client, anything that speaks JSON, but it could also be the Python Swift client or Boto or any S3 client or CyberDuck or whatever you prefer. And it goes through Rados Gateway and through as many Rados Gateways as we want, and then retrieves objects from the object store. So what's next? In OpenStack and Ceph integration, there's a few kinks and wrinkles that still need to be ironed out. So we're going to see some usability improvements as the Grizzly release draws near, and then presumably after that. That is not fully baked yet. It could be better. It could be more elegant, but it's in the works. This can, of course, use testing. So if you're spinning up a private cloud, all you need to do to build a Ceph cluster is 3 nodes, and you can build a small Ceph cluster. That's essentially all you need. And then the modifications that you actually need to make to your OpenStack infrastructure are really, really minimal. So actually spinning up a POC for OpenStack/Ceph is much less work than you might actually think. And then finally, this is a solution that is very, very interesting for private clouds. As I said, at least that's what I see or what we see in the consulting work that we do. The the people who are interested in running this sort of combination, OpenStack and Ceph, are usually the ones that are looking for OpenStack to build private clouds, OpenStack as a management for a modern data center. This is my thank you slide. If you were wondering what presentation thingy I was using, this is impress.js. And thanks to the Inktank folks for letting me use the Ceph logo. If you want to get in touch with me, those are my coordinates. My email, a short link to my Google Plus page, our company Twitter account, and obviously our website. And if you want these slides, all of this is up on GitHub. So feel free to clone that. And if you want to reuse any of this, all of this material is under the Creative Commons attribution share alike license. So please feel free to reuse whatever you want, except for the Ceph and OpenStack logos, for which I would suggest you get permission from either the OpenStack Foundation or Inktank. Yeah, right. So Mark was saying that it's perfectly fine per the OpenStack Foundation if you're doing an OpenStack talk in a community event that you can use the logo. But I am not a lawyer, so when in doubt, double check. I think I'm about out of time. Do we have some time for questions?
Probably
one or two questions. Okay. Questions? There we go. 1, 2. Perfect.
Hi. I was wondering what you suggest running as a file system under the OSDs for Ceph currently, because I know there's some suggestion that XFS and ButterFS are good choices,
yeah.
but neither are very stable.
So the OSD code has some fancy, interesting bits in there that work really, really nicely on ButterFS when it's ready. People have said that ButterFS is 2 years from production quality and always will be. I will not go that far, but I think we can all agree that it's not quite there yet. Generally, we suggest to the people that we work with to use XFS. And we generally advise people, and this is something that is generally true for Ceph OSDs, is it uses a journal writing mode. So you put the journal on a fast, high bandwidth SSD. And you put your file store on cheap 2 terabyte SATA spinners, and you slap XFS on those. And that tends to work really, really nicely. We had a question over here.
When you do a boot from volume, is it possible to define where the ephemeral disk comes from, whether it comes from Ceph or from another storage area?
If you're actually doing boot from volume, that means you have no ephemeral disk. Yes, but then it's not. So the question was, is it possible to have one? Yes, of course, but then it's not boot from volume. Then it's something that we've always been able to do, including in ISIX, where you're booting off of an ephemeral disk, and then you're attaching a volume from Cinder. And you can obviously do that. So if you're doing it the other way around, if you're actually booting off of a Cinder volume, that is exactly what boot from volume is about.
But then if you also wanted an attached ephemeral disk that was coming from somewhere that wasn't Ceph, is that possible?
I actually don't know. But in my humble opinion, if you do it the other way around, it's fundamentally the same. Isn't it?
I think the point is to be able to have stable loss and persistent data and everything, and a local really fast scratch disk. Yeah.
Okay. Yeah, I actually
use cells of different Cinder backends.
Yeah.
Right. So do a Cinder zone that's backed against Ceph, and do a Cinder zone that's backed
against whatever. Yeah.
Local SSD.
Okay. I think we're about out of time. I would love to take more questions, so by all means, just grab me outside whenever you find me. And also, we have the other Ceph tutorial. It is on Friday. I believe it is 2:20 p.m. and I believe it is in MCC 6. Do double check the schedule for that, and that is a 90-minute tutorial. Also check the conference wiki or subscribe to our Twitter feed, because we're going to announce where you can download the virtual machines as soon as someone from the conference team actually tells me where to upload them to. All right? Thank you very much.
Thanks, Florian.
Devin Ender.
Where is he?